Hi, thanks for coming. We're going to let people into the room and start in about a minute or so.
I am just to warn people, I'm really hoping that they're doing construction in our building, and I fully expect after I get 2 sentences in, they'll start a jackhammer upstairs.
Good afternoon. I'm Arun Serafin, Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. Thank you to all attendees for your support of NDIA and ETI, and thank you for joining us for today's webinar, High-Powered Microwaves 101 with Dr. Don Schiffler, a repeat performance by Dr. Schiffler. Really appreciate that, sir. This webinar is part of our Tech 101 series, where we try to distill complex technological concepts into introductory webinars for the NDIA membership with a focus on their national security impacts. Last month, we covered high energy lasers in our Tech 101 webinar. This month, we are covering another technology in the directed energy area, high-powered microwave systems. Directed energy systems, including microwave systems, have been a focus of significant investment by the Pentagon for a couple of decades and have been identified as a critical technology area by Undersecretary Heidi Shyu. These systems have the potential to protect friendly forces, including countering enemy use of drones and other unmanned systems, which have proven in recent times to be a significant threat against naval vessels, bases, and other installations. There have also been promising advancements in offensive microwave systems capable of rendering adversarial electronic capabilities ineffective. This presentation will discuss the basics of high-powered microwave technology, illustrate the importance of microwave weapons to the Department of Defense, and describe DoD and industry and government activities to develop and deploy high-powered microwave technology to the warfighter. Some administrative remarks before we get started. First, all attendee lines are muted. Second, if you have a question during the webinar, you can submit your question in the question box in the webinar panel on the right side of your screen. We will do our best to get through all the questions during the Q&A period at the end of the session. We are recording today's webinar for members unable to attend and for any webinar member who wishes to review the material at a later date, and it'll be posted up on our YouTube site after it's recorded. Within the next few days, we'll post the recording for your review. And now I'd like to introduce our speaker, Dr. Don Schiffler. Dr. Schiffler is Chief Scientist of the Directed Energy Directorate at the Air Force Research Laboratory, AFRL. He serves as the Senior Science and Technology Advisor for the Directorate's research and development of high-energy airborne lasers and microwave systems, long-range non-lethal weapons, laser communication systems, and technologies for space situational awareness. AFRL's mission is to address the technical challenges that arise from current Air Force operations, support the Air Force in developing and procuring the systems of the future, and to perform cutting-edge research on emerging technologies. Dr. Schiffler has worked as AFRL and its predecessor, the Phillips Research Laboratory, since the 1990s. His career includes experience as both a research scientist and a university professor. He's published more than 55 refereed technical papers in national and international publications. He's presided over numerous conferences, has 13 domestic and international patents on 5 continents, and led several CRADAs, Cooperative Research and Development Agreements, demonstrating the transition of research to industry and commercial and military use. Thanks again for joining us today, Dr. Schiffler, and presenting today's webinar. With that, I'll turn it over to you, and I'll come back in at the end to help with questions.
Well, good morning. Hope you guys are all doing well. Thank you for the introduction. I appreciate it. And thank you guys for taking the time to tune into the webinar. I'm going to go on and share my screen, and we can go on and get started. Presumably everybody can see that. This is the second part of DE 101. I also want to start off thanking everybody here and thanking NDIA for hosting this. I want to thank Andreas Schmidt-Sodi, who's the deputy chief scientist, who really did all the hard work in putting all these slides together from an outline. I really appreciate that. So this is installment number 2. The first installment really focused on high energy lasers. In theory, this one, I guess, should be easier for me because I started off my career in high power microwaves, but we'll see. So just a little bit of background for those of you who didn't get the first iteration. What is the Air Force Research Laboratory? The Air Force Research Laboratory is the Air Force's research labs that is there to lead, discover, develop, and deliver new technologies to the Air Force. That goes across multi-domains. I think everybody is probably tracking the stand-up of the U.S. Space Force. So we're here to serve both the Air Force and the Space Force. So one Air Force Research Lab, 2 different services. And really, when you think about the nature of where the world's headed, there are really a lot of cross-cutting technologies that cut across both air and space domains. So that really makes complete sense because you really don't want to have those stovepiped and separated from each other. So what is directed energy in general? Directed energy, at least the way the Air Force and really the DoD has been it, really fit into 2 bands. One is high energy lasers, the other is high power microwaves or high power RF. There tends to be continued debate about what the right word is, whether it's RF or high power microwaves. Most people, the joke is most people think they understand high energy lasers because they've seen Star Wars, and they think they understand high power microwaves because they have a microwave oven, and neither one could be further from the truth. And so we talked a little bit about the high energy lasers. Today we'll talk about high power microwaves. There's a couple uses, well, more than a couple, but a few ways to look at how the DoD would use high power microwaves. There is generally a gradation in effect. And this was really brought out and really, I think, really the focus of a General Accounting Office report on directed energy that just came out recently. You can see that report in its reference on the right side of the screen as you look at the screen. And I believe that is out in the public domain, so you could probably Google that and download it. But really, the way people view high power microwaves through the lens of the effects are deny, degrade, damage, and destroy. So one way to understand deny, you see a picture there, a schematic of the active denial system. People probably seen that. It was on I think Future Weapons a long time ago, at least when I still watched cable TV and wasn't streaming everything. And I'm sure you could Google active denial system and find it online. Active denial was a personnel repel. And so it was designed to deny access to areas that you wanted to keep people out of. The effect it had was it really just heats the nerves on the very surface of your skin. It's millimeter waves. It doesn't really penetrate very far. And I did the version on my palm of my hand, and it kind of felt like pins and needles, like when your hand is falling asleep. And you wake up and you get that feeling of the pins and needles. I cannot imagine doing the whole body dose. And after the thing on the palm of my hand, I decided the whole body dose is just stupid, so I didn't do it. but they definitely tested, tens of thousands of people, tens of thousands of tests, without any harm, well, other than that it hurt and you got out of the beam. In terms of degrade, damage, and destroy, a good way to look at that is through counter UAS or counter drones. And one way to look at it is in terms of the incident power on the system or its range. So if the power is low enough, you degrade its performance. That might mean scrambling the GPS, for instance, or scrambling the electronics, but you don't really damage it. Once you get closer, there tends to be a bit of a gradation in effect, where some drones you may damage them, some you may just degrade them. So you may be damaging electronics, so you kill circuits, fry circuits in the system, and of course, eventually that can lead it to be destroyed. It'll eventually drop out of the air. So this just gives you an overall view of directed energy demonstration and prototypes. You see on the left a system called Thor, which is a counter UAS system, high power microwave, sits in a Connex container. It was mobile, or it is mobile. There is a system in the center, hydrogen laser weapon system, or HELWIZ. That is hydrogen laser counter UAS. And then on the right, you see the our space domain awareness site. And why do we have that? Because we're very good at optics. We had to be to do the hydrogen lasers. And so it was a natural progression for us to move into that area. And that was done quite some time ago. So next slide, I'm going to move to that. And of course, it did not, the video is not going to play. But that video would show you a couple things. One is it just gives you a broad overview of applications. In this case, what you would have seen was a video showing computers that were in a building that was part of a demonstration for a system called CHAMP. I can't remember the acronym for CHAMP. I should, because I worked on the program. But CHAMP was a high-power microwave system that went in an air-launched cruise missile. And so the good thing about CHAMP was the following. It could address multiple targets in one single sortie of the weapon. So the cruise missile would say, go by a building, fire the microwaves, go back to the next building, go on another building, fire microwaves at it, and then you would have effects on the electronics in the building. What this video would show you would be all the computer screens going blank. And so in that sense, it's kind of a, high power microwaves are kind of useful because you would see typically you get the blue screen of death. So the question is it high power microwaves or is it just Microsoft? Sometimes no way to know. And so so in that sense, it's a very handy technology in that regard. In the case of this video, that was a case where you disrupt the computers. You don't necessarily destroy them or cause permanent harm. So it's kind of effect that requires human intervention. The other good thing about CHAMP system, and I think we might talk about it a little further on, the other good thing about CHAMP is it did not require a PhD to run it. The whole test was done by airmen and pilots, and there were no PhDs in the way or even around except to take pictures. And so that I would consider a successful transition of any weapons system, but definitely directed energy. So again, no PhDs involved. Good thing. So the way we view directed energy, the way the DoD views it, is that they're necessary for the future contest environments we face. And so you see some systems here, both past, present, and what's coming up in the future. So you see the top slide there, and that has the acronym for CHAMP. That shows you the CHAMP missile, and the high power microwave system is mounted in that missile. And again, it's an air-launched cruise missile. You see a system called Max Power. Max Power is a high power microwave system that was designed for counter IED, and that was actually deployed in the Middle East. And so it was, I can't remember where exactly it went, but it definitely got over to the Middle East in a real operating environment. And then below that, you see the active denial system. You see an earlier version than the one you saw the cartoon of. Center system is Thor. Thor is the tactical high power operational responder. It's a counter UAS system. And some notes about Thor that in our mind made it impressive. The microwave system on Thor is something called a relativistic magnetron. And the nice thing about that system is it reflected a consistent basic to applied research investment on the part of the Air Force over a number of years. And so we viewed that as very much success, because although it took a while, we were able to take a system from a basic research idea and turn that into a real operational system. And then on the right, you see the Chimera system. Chimera, you can read the acronym. It's an air-based defense system. So think about something to say going after UASs at longer range than a Thor system would. And so that's the progression of where we're headed. And so another thing to note here, you'll see the obvious trend. We're starting to look more at ground-based systems, partly because they're portable, partly because of the problems we have to worry about. So next slide that I'll go to. So the things we have to, the challenges we face in high power microwaves, it's everything from the component level up to the effects on the target and understanding what those effects are, and to some extent also the atmosphere. It's not quite so much a problem with high power microwaves or with high energy lasers. And so we don't really face quite the same difficulty problems. But let's talk a little bit about the components and the high power microwave effects. Component science. We have the obvious problem. I think everybody remembers, or if they had them, they're old enough, they remember the first cell phones. They were brick phones. They were huge. Now, we eventually went to flip phones, which were really pretty small. Then things kind of got bigger with smartphones, but smartphones had a lot more functionality, so they grew in size. But nevertheless, think about the trend in the computers that drove smartphones. Think back to when you had a mainframe, and now we have that computing power and even more in a small phone. So the general trend is to want to make things smaller. That is problematic for high power microwaves. High power microwave device works. There's really two classes: vacuum electronics and solid state. You don't get a free lunch either way. Talk about the vacuum electronics a little bit. Typically what you're doing is in vacuum, and it's what you might think about from the 40s and 50s about vacuum electronics. You have an electron beam. It's emitted by some field emitter or cathode. Electrons come off the surface. You create bunches of electrons, and then you take the energy out of those bunches and you radiate it. All that's done in vacuum. And the voltages there are significant. Think about hundreds of kilovolts and tens of kiloamps. That's really only lasting for, say, hundreds of nanoseconds. So, a tenth of a millionth of a second. It's not very long, but it's still a lot of power and voltage and current to deal with. So you have significant material problems. You have significant problems in generating those voltages and currents in a small package. And then once you create the power, the microwave power, it's typically on the order of gigawatts or higher. That's pretty daunting. However, that is also in a very short time frame. Nevertheless, you have significant challenges with the materials. So while the physics of the microwave device are really interesting, and I love them as much as the next guy, the real advances and the real problems are in the materials area and the component science area. The same goes for solid state high power microwaves, where you may be wanting to rapidly switch, use a solid state switch to create rapid switching at a microwave frequency that allows you to generate power that's coming from, say, a high energy density capacitor. So that is also challenging, again, because we're asking a lot of the materials. There's some other things that go along with this. Energy storage is a big problem. So we have to be able to, and this holds also for high energy lasers, you have to be able to store the energy, generate it, and then condition it and put it into the microwave source in a format that's useful to you. So things like high energy density capacitors are a really big deal, particularly for high power microwaves. The effects, that's another problem right there. It's a very complicated environment. So think about a building. It's populated with computers and populated with, probably people in there. And high power microwaves hit that building. They're not going to have any effect on the people. The pulse is just too short, but they'll have an effect on the electronics. Think about, I'll use an analogy of my house. My cell phone reception in my house was really poor from room to room. It could be great in one room, horrible in another, until I got an amplifier for my house, put an antenna on the roof, did all that stuff. And so it's the RF environment of a building can be very complicated, and understanding how high power microwaves propagate into that room can be very difficult. Construction materials are important. Windows and where they are important. And so understanding that complex environment for a target can be important. And then we have the other effect of we have to couple that power into a piece of electronics. And people had the annoying habit of moving computers around and doing stuff in their offices and all the stuff people do. So you need to understand really what is a very stochastic and random environment, and how RF is going to propagate in that environment. And then you have the added problem that electronics are advancing rapidly. So I think most of the effects guys who do this work in all the services kind of feel like they're trying to catch up with a fast moving train, and it's really hard to get in front of it because the advances in electronics are progressing so rapidly. So I think I just already addressed some of this. A major limitation of high power microwaves is electric field breakdown. So we all kind of understand breakdown. Think about when you drag your feet on a carpeted floor in the winter and then touch a doorknob. That's a good example of electric breakdown. For those of us who are electrical engineers at some point, I remember when I was taking labs, I had a T-head, it was dread fear that you would have static electricity on you, and then you would pick up a CMOS or something like that. So electrical breakdown is a significant problem. What you see on the right is something called a Marx generator. What does a Marx generator do? That effectively takes power, relatively low voltage, high current, and transforms that into high voltage and really high current, but at a short pulse. And so what you see there is it'll take, think about a charging time in the order of seconds. And then what that Marx does is that allows you to take something in the order of seconds and give you a high voltage pulse compressed into something like 100 nanoseconds. So 100 billionths of a second. So very small pulse. It's effectively power conditioning. So what you see in that picture are things like switches. Those green things you see there are resistors. Behind that, you can't really see it well, but there's some white things that look like bricks. You kind of see them at the bottom of the holder. Those are the high energy density capacitors. And so that's what's kind of secondary energy storage that then gets switched and and put into a microwave source. And then you see all the other stuff that goes with it, to move power around. So that is not very big. That's something that, kind of one person, two people could pick up. Think about something the size of your desktop computer box. So pretty small. That's a lot of current voltage for something that size. So one thing we worry about a whole lot are materials that can withstand high voltage, high current, both in the bulk and on the surface of the material. So this sounds like a advertisement for material science, and it is. So some of the things we're starting to look at, we really want to take advantage of advances in materials. So we spend a lot of our time looking at advanced materials. There you see some barium titanate, some pretty pictures of a barium titanate composite. We have been, all the services, but the Air Force in particular, have been heavy investors in modern computer simulation techniques. We put significant effort into modeling materials, particularly modeling new materials that we can design that will have good voltage standoff properties, and then actually turn those materials that are generated on a computer into reality. And in that case, you actually see, you can actually see that. You see what it looks like at the atomic level on the bottom, where they talk about stuff called surface functionalization. Surface functionalization is a fancy word for crap that's stuck on the surface of a material. And that is a significant breakdown problem. So we can do things like model that material. We can then take it from the atomic level to the intermediate level, where you're talking about, particles and say stuff that's on the size of a micron. And then we can actually turn that into reality. Another thing we worry a whole lot about is emission of electrons from materials. We have to create a beam of electrons in vacuum. So we spend, it sounds like we're going back to the 50s, and maybe it is. We have to spend a significant amount of time worrying about field emission and how electrons get pulled off materials. So that's also another significant research investment on the part of the whole community. So I think I've kind of described the basics of the system. I'm going to go back over it one more time. The key parts of it are the prime power, and how do we think about basically what's coming out of a wall plug, and then how do we condition that and transform it into something that is high current, high voltage, short pulse. How do we turn that into microwaves, either through creating an electron beam that propagates in some kind of microwave structure, or just through switching to a solid state device? And then how do we radiate that out into the atmosphere? And then how do we, and once we do that, how do we propagate it to a target? And then how does those microwaves interact with that target? So that's kind of the whole of, it's almost interchangeable with high energy lasers. It's just a different effect on the target. Where high energy lasers are burning a hole in something, typically, high power microwaves are not burning a hole, but they're doing something to the electronics. And so but otherwise, kind of the big problems are still the same. We still have to worry in both communities about things like prime power, energy storage, atmospheric propagation, just at different wavelengths and frequencies. We still have to worry about target interaction. Again, just different wavelengths and frequencies. But a lot of the same mindset can be carried over between the two. And in some ways, that's kind of helpful because one community can learn from the other. So I think that's all I have. And I guess I can open things up to questions.
That's great, Dr. Schiffler. Thank you for the presentation. Please submit your questions in the question box on the side of your screen. We've got questions coming in now. I have a couple. Let me ask you a couple here. So first is, could you talk a little bit about what the technology is to focus the beams And then what is the potential for collateral damage from these kinds of systems?
Sure. I'm going to go back a couple slides. Let me see if I've got one where I can get a good. We typically worry about antennas to do the beam focusing. So when RF comes out of a microwave source, it's basically a plumbing problem. RF engineers will cringe when I say that. But you have to get the power out of the source, typically into waveguide, and then we propagate into we put it into an antenna. So on that far left where you see the Thor system, you see a dish antenna. I mean, it's a dish antenna. So you have if you look at that closely, that's an interesting antenna. You see something that kind of looks like an elongated cylinder. That is actually a very fancy bag filled with sulfur hexafluoride, which, yes, is a greenhouse gas. It's also very good at stopping RF breakdown. And so behind that bag, you have a primary, think about a primary radiator that has most of the high power. And then that radiates, that effectively bounces back off that dish. That's the thing you see that's not in the bag. And that is, that's what's radiating out. So rather than radiating out in every direction, think about that dish is the element that does the focusing. And so it's really kind of the technology. It's a fancy version of the technology we've been using for RF since World War II.
For radar systems.
For radar systems. Yep. Kind of just like a radar system. Not like a radio. Well, it's not like a commercial radio station where you're broadcasting in all directions. It would be more like a radar system, or think about microwave links where you're trying to beam microwave comms from point A to point B.
Okay, second very basic question. Help us with the analogy between the microwave source we have in our kitchen and the microwave source that you're talking about here. What's the power difference, energy difference? What's the size differences, those kinds of things?
Yeah, so usually the thing in your microwave oven, I think there's something called a Magnacon. They churn them out by the hundreds. It is a very small microwave source. You can hold it in the palm of your hand. It will typically give you hundreds of watts to 1,000 watts of power, and it obviously just runs continuously. Put in 2 minutes to warm up whatever you're warming up, and it runs that whole time. And think about your you put your food in the microwave oven and close the door. You form now that box is something called a microwave cavity. And so those microwaves, if they do the microwave oven design right, they will tend to be focused right where your food should be on the little thing that's spinning around. So that's kind of the power level. It's really not meant to radiate it, although PhD students who I know, one I know well, might have taken a microwave source out of a microwave oven and done something not radiated into the microwave oven, but I would never admit to that. Now, to give you a feeling, that is actually pretty energy and power intensive when you think about it, because it runs for seconds, right? And it's 120, I don't know how many amps currently they draw. It's a fair amount of power. The high power microwave sources we're talking about here, let me step back a second. Those things in your microwave oven, tens to hundreds of volts on the microwave source. High power microwave tube here, think about 300,000 volts, 300 kilovolts, rather than milliamps of current. So rather than the few thousandths of an amp of current, think about 10,000 amps of current. However, the way you get away with that murder is that you're only doing it for about 100 nanoseconds, so 100 billionths of a second. So that's how you get away with that without catastrophic consequences. it's because of that time difference. However, still the energy storage problems are pretty significant, because there's a big difference between the size of a microwave oven and that Connex container you see on your left side of the screen.
Okay, lots of questions. Tell us about the countermeasures, right? To, if you know, if we're faced with microwave systems,
Mhm.
what do you use to protect our systems against microwave systems?
Yeah, that's a good question. So there's some obvious ways to do it. One is just put everything in a metal box, because no microwaves or anything else can get into the metal box. If you force people to do that, you've kind of won, because nothing can get into the box, but nothing can get out of the box. So in that sense, it's kind of a win, right? Because you've got to have some way to communicate out. Now, the next thing you say is, okay, well, you got to put a port in there somehow. There's got to be a window or something to communicate out. You could say, you could harden that window so it can transmit every other frequency you want to transmit, but the place where the microwave weapon is working, it won't transmit. So yes, you could do that. You could do that using filters. There's any number of ways. However, there you've kind of also won too. It's almost like a it's this measure countermeasure type problem, because all the microwave source designer has to do is change their microwave source. However, then you may well force people to change 100, 200 buildings, whereas you may only have to change 5 to 10 microwave sources. So again, it's the countermeasure thing. The cost curve tends to be in your favor if you're the person doing the attacking.
Okay, slightly more technical question. You talked about the size of the power systems required, right? The energy issue. What about cooling? Is the high density cooling a challenge for these microwave systems?
It depends on the system. Most of the systems that I've talked about here, the average power is actually low enough that thermal management's not that much of a problem. The one area, however, where thermal management is a big deal was with the active denial system, because there you did have a higher average power. So in that case, you do have to worry about it. Thermal management is not quite as much a problem for high power microwaves as it is for high energy lasers. Part of that's also efficiency of the source. You generally don't have laser systems that are 50, the overall system, 50 to 60, 70% efficient. With high power microwaves, partly because they've had a lot more time to work on it, there are a lot of, I'll call them tricks. There's ways to make those systems more efficient. You could probably also argue the physics is more in your favor, and so you're not throwing away as much wasted power into heat.
So on sources, you mentioned magnetrons, Marx generators as HPM sources. What are there other sources that are in development, or that are other sources that are widely used?
Oh, there's a whole, I'll use the word, there's a whole zoo of them. So really what dictates your choice of a microwave source? It's a couple things. If you look at it from the system design point, it's going to come into what we would call SWAP, size, weight, and power. What can a system designer fit into a given package? I used magnetron just because it's easy. I say easy. Actually, it's not really easy, but it's one that typically that people have worried about. There are other things that are traveling wave amplifiers, there's backward wave oscillators, to throw out, some names. The basics of these sources were all explored in the 40s, 50s, 60s. it kind of went away. And then, at the advent of modern computing, people have been able to take the next step and really push the technology further. Excuse me. But it really, comes down to, what does a system designer need? And then how advanced, another thing we have to worry about is how advanced is the technology that supports it. The source may be great, but if I have to place some odd demands on the, say, the prime or pulse power that can't be met with current, state of the technology, one may want to rethink what you choose.
Okay, what's the feasibility of using high power microwave systems in space?
It's certainly, here's a good thing about space. There's no air up there. And why is that a big deal? There's no air, you don't have to worry about air breakdown due to RF. So, so in a lot of ways that might make your system easier, in the sense that you don't have to have things like that balloon you see on the Thor system, because you might not have that air breakdown problem. But then you might have other problems that have to do with the surface of the antenna. Is that going to break down in a space environment? Space is just an ugly environment. We know this in spades, from our space domain awareness and space situational awareness group. So, the fact there's no air is a good thing, but also the fact there's no air could be a bad thing in terms of breakdown problems. I suppose the other thing you'd have to worry about is how do you get it into orbit in the first place? And so I can't say I've really thought through that, but I'm sure you'd have some kind of a payload problem, and all the other problems you have with satellites that are up there for a while, and maneuvering around and all that other stuff. You'd have all those problems you have to face.
How about undersea, or from above surface down under the surface of the water?
The good thing, well, it depends on who you are. The problematic thing about water is microwaves and RF don't propagate well down into water. So you'd have to be really, really close to whatever you're going after. I suppose you could use really low frequency to do it. I know they do comms that tend to be hertz to 10 hertz frequencies, but then the systems become just gargantuan. They're huge. One way to think about the size of a microwave system is the way they scale with size overall is take the wavelength. So let's say we want to operate, or frequency, let's say we want to operate at a gigahertz, which is about a 10 centimeter wavelength. So the typical scale size of everything is about 10 centimeters. But if you wanted to go to much longer wavelength, everything is going to scale with that size. So things just get really big.
Question about our competitors. Where do you see the capability of the Chinese and Russians in these kinds of high-powered microwave systems?
Yeah, I'm going to date myself. I did my graduate student work during the end of the Cold War, and so so it was always kind of an even race with the Russians in the 80s and 90s. That kind of tapered off with the, I guess I should have said Soviets. It kind of tapered off with the fall of the Soviet Union, but Russia is definitely, you certainly see more articles from Russia in the open literature. And so they're back to doing research and publishing. You definitely see the Chinese working on this. I gotta imagine you could probably pull open Applied Physics Letters or Journal of Applied Physics or IEEE Transactions on Plasma Science. You could probably open the latest issue and see papers from China in that issue. And I will say that China, Russia's always been really good at it. They've been good at it since the Cold War. And to give the Russians credit, the Soviets were the first ones to come up with the idea of high power microwave systems. the Chinese they've learned a lot from both Russia and the US. And so they're coming up with some really innovative ideas. It's when I get a chance to actually read a journal article, they tend to have very well written papers. I will say the Russian papers tend to be as opaque as they were during the Soviet days. They'll start off with equation 1, and the normal human would have equation 2, 3, 4, 5, 6. They just go right to equation 10. Nothing's changed in that regard.
Okay. What is the range of high-powered microwave systems? And we'll start with that one.
Sure. So they can a whole host of ranges. It kind of depends on the size. So I can't give you a firm answer, say 30 meters, because it depends on how much power you're radiating in the target. So really what you have to ask is, what is the mission and what are you trying to do? You may have people who are perfectly fine with an engagement distance of, say, 30 to 200 meters. And you may have other warfighters who are like, are you out of your mind? I don't want the UAV that close to me. Make it go way farther away. So then you may be talking about 2, 3, 4, 5 kilometers. Again, depends on the customer, the mission, and the source. But there's obvious constraints, right? You got to have enough power to project at range and cause an effect. But you don't want an antenna that's the size of a football field. So it gets into design trade-offs.
And in the other part of the directed energy space, when you think about high energy lasers, there's always this discussion about, if you miss the target or you shoot past the target, are you going to have an effect on things behind that target?
Right.
That's the issue for lasers. Is it the same issue for microwave systems?
It depends on the situation. So one thing that was talked about, for those of us who've been in the Pentagon, originally there's the idea to put Thor on the roof of the Pentagon, and for counter UAS, and you could easily do that. So we did some careful modeling to say, what is the keep out range where you would have an effect on something other than the target you want to impact. So it's not unlike radar. You don't want to be standing right in front of the radar dish. So there's some keep out zone, I guess is what I'm saying. And you want to be outside that keep out zone. You want to be outside that focus beam. The good thing about microwaves and RF that lasers, at least in terms of collateral damage, is that things drop off much more quickly with distance. It's that 1/r² problem. So the power drops off 1 over the distance squared. And that, in terms of collateral damage, is really in your favor for high power microwaves. So you don't have quite that problem with high power microwaves as you do with lasers.
Another question on how many shots can a system shoot at once without a recharge?
I'm going to give you the answer that's kind of like the other one. Depends on the system. Why does it depend on the system? It depends on how much energy you can store in effectively a buffer. So the system on the cruise missile, you're probably talking single digit shots before you got to do something. With a system like Thor, it's bigger. You could have a generator there. I don't know, a diesel. Maybe you could have it plugged into shore power, where you have effectively a power plant behind it. In that case, you could probably tolerate more before you'd have to recharge. I don't know, hundreds to thousands, depends on the size of the spigot coming in.
Okay, one more slightly technical one, then I have a couple of mission-oriented questions. Can you use any type of repeater to extend the range of these systems?
Yeah, this is people talked about this. You could in theory, but because of the nature of the way high power RF spread, because of the way microwaves and RF spread out, you probably lose more power than you would think. You'd have to have a very big, effectively repeater or receiver antenna. So you could do that. And we've talked about that. It's never been clear exactly what you gain. It doesn't work quite as well as it does with lasers, where you can have a relay mirror. Because of the laser, you can have a much more focused beam. And then you could bounce stuff off a mirror that's on, I don't know, a blimp or balloon or something like that. Just doesn't work quite as well with RF because it spreads out more.
Just to clarify something you said earlier, you're talking about modeling and simulation for simulating materials properties. The question is, who develops and owns the 3D COMSOL model that you referenced?
Good question. I'm not sure I know. I'd have to go ask. I think it's probably the Air Force Research Lab. But I'd probably want to check. And the reason I want to check is we collaborate very closely with the other services in lasers and in high power microwaves. So there's a lot of open comms and sharing between the S&T communities and all three services, which is a really good thing, by the way. And so we'd probably have to check. It's probably Air Force, but could be Navy.
Are there other modeling and simulation tools of choice that people in the field are using right now?
Oh, yes. So in terms of the materials modeling, geez, now I'm drawing a total blank on the computer codes they use. There's very well-known materials modeling codes that our materials modelers use. The Air Force, well, really all the services tend to use a framework called Galaxy. Galaxy is a really interesting software framework. It effectively allows us in one single package to simulate a microwave system from wall plug to the effect on a target. And that has different computer codes that plug into it that kind of orchestrate that. I know that for the prime and pulse power, they use SPICE, which is kind of a standard electrical engineering model. For the microwave systems, they typically use a code called ICEPIC. That's an acronym that I don't recall what it stands for. And then for the propagation part, they use a code called JREM, which I do remember, Joint RF Effectiveness Model. And it's what it sounds like. It's an effectiveness model, tells you how well it handles everything from the antenna to an effect on a target. So it'll do all that RF microwave propagation out of the antenna through the air into, say, a building and into a box in the building, and then tell you the probability of effect on that box. And so all services use that JREM model, and JREM is actually used. This is another good thing. It's not just used by PhDs. Targeteers can use it too. So the warfighter can use it. You don't really need a PhD.
Okay, we're coming in for a landing here, so we need a bit of a speed round here. This is a curious one. Havana syndrome. Any implication on high power microwave systems for that whole experience?
I don't know. The National Academy has one opinion. I've read their report. I think they said it was crickets. Literally said it was crickets. Other people say it's RF. All I can tell you is there's definitely something happening. It's just not, it's just not clear to me it's directed energy. There's something happening. I don't know what it is. I don't think it's crickets.
Could you talk about the mission set that's most viable for the microwave systems? There's a lot of questions and talk about counter UAS.
Mm-hmm.
There's frustration that we haven't deployed counter UAS systems as quickly as we'd like. Talk about microwave systems as potential counter UAS system and what you think are the most promising systems under development for that mission.
Yeah, so what's a bit maddening, what are good applications? Well, I showed 3 of them. And one it was the counter IED. There's a counter UAS system. You see it in the picture. You see a counter electronic system. That was the one on the missile. Counter personnel, which is active denial. I think the big obstacle we face is that, so these are all systems that have been demonstrated. They exist in prototypes, and I share the frustration they have not been used. Probably more than anybody in your audience. So I think the real problem is not the technology. It's something the DoD calls .mil-PF. What is it? Doctrine, operations, training, maintenance, logistics. I forget what the rest of it is. It's not the technology. It's everything that goes into supporting that technology and making it work. And that is what the DoD is starting to work through right now. So hopefully we work through those problems. And to be honest, there's also a fear of the new, right? We kind of understand how bombs work. We've been dropping them for a long time. I talked about the misconceptions about direct energy, high energy laser, high power microwaves. People think they understand them and they don't. And it's because of that false sense of understanding, people have misperceptions. A good one photon hits me from a laser, I'm going to be blind. Well, probably not, because you're getting photons in your eye all the time. One bit of RF hits me, I'm going to get cooked. Well, you know what? You're awash in a sea of RF. There's radio transmitters, cell phones, microwave towers. It's all around us. But the fact that you can't see it is what makes people uneasy. And so getting through things like doctrine, policy, etc., and getting over the fear of the new is what we have to do. That's controversial, by the way.
But that's a good place to call it right now. Appreciate all of the questions. We are sitting on too many to answer now. And appreciate you answering those questions, Dr. Schiffler. I will close the session by thanking everyone for their attendance and all the great questions. We're going to post this recording as soon as possible online. If you have feedback about the Tech 101 series, especially topics you'd like to see us cover in the new year, please email us at eti@ndia.org. I also want to take this opportunity to highlight a few upcoming and recent ETI activities. On Monday, December 11th, ETI is working with the Hudson Institute on a one-day symposium looking at the technical challenges to achieving systems interoperability. This is an in-person event in Washington, D.C., with speakers from the Chief Digital AI Office, CDAO, the Office of the Undersecretary of Research and Engineering, as well as the Undersecretary for Acquisition and Sustainment, Office of Naval Research, and many industry experts. We're proud to be sponsored by Tangram Flex for this event. Registration is limited, but it's open now on the NDIA website, so please look there. ETI just released 2 new reports, both available on our website, as well as podcasts on these topics on our Emerging Tech Horizons podcast, which is available on YouTube, Spotify, and other platforms. One was on modernizing defense microelectronics, which looks at possible improvements on the way DoD buys its microelectronics, and another on enabling the joint warfight, which was based on a series of webinars hosted by former Deputy Undersecretary Al Schaefer, which looked at the technologies and concepts which will shape the future of joint warfighting. So we commend both those reports and the podcast to you. The next session in our Tech 101 series is next year, January 30th at 1 p.m. Eastern. That's Digital Supply Chain 101. Please Mark your calendars for that. Registration will be open soon on the NDIA website. Additionally, please be on the lookout for the release of our new directed energy supply chain study shortly after the new year. In this study, we assess the state of supply chains for the kinds of systems Dr. Schiffler was talking about today, directed energy weapons, and we provide some actionable recommendations to improve their health and resilience. With that, I want to once again thank Dr. Schiffler, and thanks everyone for joining us today.